Hello, algebra students. These are going to be your 11.3 notes. We're going to talk about how to describe the shapes of data. First, here, go ahead and pause and copy down the notes into your spiral notebook. So these three graphs are histograms. You should have created histograms either in your 6th grade or 7th grade class. We'll go over how to create them again today. But a histogram shows the shape of a distribution. In 11.2, we did box and whisker plots, which shows the spread or the variability of the distribution. Now we're going to talk about the shape of the distribution. So symmetric and skewed distributions. We have skewed left, skewed right, and symmetric again. These are the same as your histograms. If your histogram was skewed left, that means the tail, remember how the whisker was longer on the left? For a histogram, it means the tail goes down to the left, and most of the data is on the right. If you have data that's skewed right, that means your tail is on the right, or your longer whisker is on the right, and most of your data is on the left. And if you have a symmetric distribution, it means it's basically a mirror image of each other. If you draw a line down the middle, you can see that this is basically a reflection on either side. It's pretty equal. And remember, for it to be symmetric, it does not have to be 100% perfect. It won't be 100% perfect most of the time. It just needs to be pretty close. So we have data that can be skewed left with the tail going to the left, data that's skewed right with the tail going to the right, and data that is symmetric where it's pretty equal on both sides. So for our first example, we have a frequency table here. We're going to talk about those in a second because you're going to be responsible for creating your own frequency tables eventually. And we want to create from this frequency table, we want to display the data in a histogram. So we want to create a histogram for this data. A frequency table is basically a table, but it's called a frequency table because of the fact that part of the table is 100% the frequency. So this is the number of tickets sold, 1 through 8. So if you sold 1 through 8 tickets, how many people did that? 5 people did that. If you sold 25 to 32 tickets, right? If you were a student and you were selling 25 to 32 raffle tickets, how many students did that? 25 students. So the frequency is how many times it happened. So what we are going to do is we're going to take this data and create a histogram with it. Just like all graphs, we need a title. Raffle tickets is what this information is about. So that is what I'm going to make the title of my histogram. Frequency is always going to go on the y-axis. Excuse me. Frequency is always going to go here. The number of tickets sold is going to be your x-axis label. So title, labeling the axes, and then we can go ahead and start giving them numbers. So the lowest frequency that we have is 5, and the highest frequency that we have looks to be 25. So I'm going to go by 5s. 5, 10, 15, 20, 25. For my labels for my y-axis. Choose the intervals that make the most sense for your data. The great thing about your x-axis is the intervals are already chosen for you. That's why this is called a frequency table. Your intervals have already been given to you, so you just need to write them along your x-axis. So we have 1, 2, 3, 4, 5, 6, 7 intervals here, so I'm going to do my best to create 7 equal spaces down here. So I'll go 1 through 8, 9 through 16, 17 through 24, 25 through 32, 33 to 40, 41 to 48, and 49 through 56. So I kind of made them a little squished there. I should have probably moved this title down, but either way, it doesn't really matter. So for each one of these intervals then, I'm just going to draw basically a bar graph that goes up to the frequency. So 1 through 8, I had 5. 9 through 16, I had 9. You want to make your bars pretty much as equal as you can, and they have to be touching each other. This is a histogram, not a bar graph. This data on the x-axis here is continuous. So you want to have your bars touching, unlike a bar graph where they're separate. 17 to 24 is 16, so it's going to be like right here. I'm not doing a very good job of making my bars straight or even. But if I had graph paper, I would be doing this on graph paper. Then I've got up to 25, which is here. And then this is 20, so here. Eight, maybe down here. And 7 here. So there is my histogram. So a couple things about histograms. We'll talk more about how to create your intervals in a minute. But just a couple things. Your bar's got to be touching. Frequency is always on the y-axis, and then everything needs titles and labels. So now let's describe the shape of this distribution. The easiest way to describe the shape is to draw a line down the middle and compare the two sides. Well, even though, yeah, these over here are much lower than these, pretty much, it's pretty symmetrical. There's no tail to speak of. So the shape of the distribution is going to be symmetrical. So remember, a tail kind of looks like this. You can see it's a big hump, and then it kind of tails off. A big hump, and it tails off. Our hump here is in the middle, not on the right or the left, so there really isn't a tail, so this one is going to be symmetrical. Now, depending on what type of shape your data has, you can choose different appropriate measures that would be the best for conveying information from your graph. If your data distribution is symmetric, you will use the mean to describe the center and the standard deviation to describe the variation. So if I give you data and you graph it and I said choose the appropriate measure of center and variation to describe the graph, and it was symmetrical, you'd have to do the mean and standard deviation. If your information is skewed either way, right or left, you are going to use the median to describe the center and the 5-number summary to describe the variation. So if you haven't already, pause, write this down into your notes. Then we'll get on to example 2. So a police officer measures the speeds in miles per hour of 30 motorists. Here we just have a regular old table of information. We want to create a histogram from this table. I want 6 intervals, and they're going to begin with 31 through 35. So, what I'm going to do, this here is my frequency table. Shh. Sorry, guys. This is my frequency table. So if I'm going 31 through 35, when you're creating your frequencies, you cannot have any overlap. So if this is 35, this next one's going to start at 36. Now, how do I figure out what the rest of the frequencies are? This one is 31 to 35, so that's 31, 32, 33, 34, 35, 5 numbers. So 36, 36, 37, 38, 39, 40, 36 through 40, which means the next one is going to be 41 through 45, 46 through 50, 51 through 55, and 56 through 60. They have to be completely equal. So they each have to contain 5 numbers and there can be no overlap. Now what we're going to do is we're going to use our table to figure out the frequency. How many people were driving from 31 to 35 miles an hour? And it looks like 1. How many people were driving 36 to 40 miles an hour? 1, 2, there should be 3. I'm missing one. 3. How many people were driving 41 to 45? 1, 2, 3, 4, 5. How many people were driving 46 to 50 miles an hour? 1, 2, 3, 4, 5. $46 to $50. I have 6 on here, but it should be 5. 53. Got the other one here. So 6, 51 through 55 miles an hour. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then how many people are driving 56 to 60 miles an hour? 1, 2, 3, 4. So we've got our frequencies. So we're going to make our histogram just like we did in example 1. So give it a title. This particular one is about driving speeds. Frequency is always along your y-axis. Your x-axis is going to be here, so this is going to be speed, specifically miles per hour. And then let's go ahead and make our bars. So we've got frequency goes from 1 to 11. So I think I'm going to go 2, 4, 6, 8, 10, 12. And then 31 to 35, 36 to 40, 41 to 45, 46 to 50, 51 to 55, and 56 through 60. So we have 1 for here, 3 for here, 5 for here, 6 for here, oh, that's not very straight, whoopsie, 11 for here, and 4 for here. Okay, so part B, which measures of center and variation will best represent this data? If I'm looking at this data, it kind of seems like it has a tail going off to the left. Most of the data, the biggest bars, are to the right. So this data is going to be skewed left. So that means the median will be the best measure of center, and the 5-number summary will be the best measure of variation. It didn't actually ask us to find these, it just asked what they are, which was shown from this here. So part C then says, the speed limit is 45 miles an hour, so how do you interpret these results? So where does 45 miles an hour fit on this graph? This is 41 through 45, which means this line is basically 45 miles an hour. Well, looking at that, and looking at the number of people driving slower than 45 miles an hour and the amount of people driving faster than 45 miles an hour, we have bigger bars, which means we have more data to the right. So that means more people were driving faster than 45 miles an hour. So by looking at the histogram, and we can also look at it on the frequency table. So your 45 miles an hour is going to be here. So 1, 3, and 5 people versus 6, 11, and 4 people. Most of our data is above 45. So most people were speeding. If the speed limit is 45 miles an hour and most of our data is above that, that means most people were going faster than it. So most people were speeding. So example 3 says emoticons, basically emojis. I guess emoticon is like the technical term for it. So emojis are graphic symbols that represent facial expressions. They're used to convey a person's mood in a text message. We have a double histogram over here. You can see one on top of the other that shows the distributions of emoticon messages sent by a group of female students and male students in 1 week. So the reason that they are two different is because it's female versus male. We want to compare the distributions using their shapes and appropriate measures of center and variation. So first, let's determine the shapes of the distribution. On top, we have the female students. And let's look here at the shape of this distribution. It definitely looks like most of the data is in the middle. It doesn't look like there is a tail on either side, so I'm going to call this symmetric. Male students, you can easily see that most of the data is on the left, causing this tail to go off to the right. So that is going to be skewed right. So compare the distributions. So we just used their shapes. Female students are symmetric, male students are skewed right. So we got the shapes. Appropriate measures of center. Well, for the female students, we would use the mean to describe the measure of center for female students because it is symmetric. So where would the mean take place? Your mean is going to be pretty much like right in the middle of your data. That's why it's used for the measure of center. So that's probably going to be somewhere here. So that's going to be somewhere in the 30 to 39 range. And the reason that I put that there is because we want to go right in the middle. Going right here, which would be smack dab in the middle of the graph, would be great. But if I really look at it, this bar is a little higher than that bar. This bar is a little higher than this bar, and this bar is a little higher than this bar. So the mean's probably going to be a little bit further to the right. Like I said, symmetrical doesn't mean 100% symmetrical. We would use the median to describe the measure of center for male students. So where would that lie? Well, let's take a look here. We got like 14 people and 12 people, and then it goes down here, way down here. It looks like 6 and 2, so that's 8. And probably say somewhere here. So once again, we're not just cutting the bars in half, going 2 bars, 2 bars, right? Most of the data is over here. We want to go right down the middle. So this is going to lie within the 10 to 19 interval. So now that we've compared them using the appropriate measure, now that we have found the appropriate measures of the center, how do we compare them? Well, what this means, so this is the important part. From this, we can conclude that a typical female student is more likely to use emoticons than the male student, right? Because our measure of center for the females, which is the mean, would lie within the 30 through 39 range. The measure of center for the males, which would be the median, would be the 10 to 19 range. Plus, you can kind of just look at the graphs and determine that. There are way more males using 0 to 9 emojis per week, and there are way more females using 30 to 39 emojis per week. So even the graphs just pretty much tell you that a female student is more likely to use emoticons than a male student. So, measures of center, check. Now, let's talk about the measures of variation. Once again, females were symmetrical. We would use standard deviation. I'm just going to abbreviate it SD because I'm kind of running out of room here. To describe the variability for females. And we would use the 5 number summary to describe the variability for males because their data was skewed. Then let's look at it up here. The variability is basically your spread of data. If we were to actually be able to find the standard deviation 5 number summary, we could, but just given this information here on the graph, we don't know what the exact numbers are, so we cannot find the actual standard deviation or the actual 5 number summary. So instead, I'm just going to kind of look at the graphs and look at it, and I'm going to go ahead and conclude that the data for females is more varied or spread out than for males. You can kind of look here, the females go across all these, 0 all the way up to 59, and the males are kind of stuck here in this region. So what does that mean? Meaning that female students' use of emoticons tends to differ more than males. So your female students vary more than your male students. Lots of information here, lots of things to write down. For your conclusions, which were this piece and this piece here, you can use your graphs to look at it. The rest of it was just putting into words the information from, where is it? Here, telling us what are the best measures of center and measures of variation for what type of graph. Okay, you can go ahead and pause here again and write it down. So a bell-shaped distribution happens when it is approximately symmetric about the mean. Don't worry about in a future course. For now, all we care about are these following rules to help us see how standard deviation really is helpful as a measure of variation. So if it's on a bell curve, that means that 68% of the data lies within one standard deviation of the mean. So here's your mean, right here. A standard deviation is given by this symbol. So a standard deviation up and down, so one standard deviation in each direction, and you have 68% of the data in there. If I go 2 standard deviations, so 1, 2 to the right, 1, 2 to the left, 95% of your data is going to be within there. And then if it's more than 2 standard deviations from the mean, it's data that is considered unusual. It's almost like these outliers way out here, like who knows what's going on. So because the data is symmetric, we can say that basically 34% of data lies within one standard deviation to the left and one standard deviation to the right. And then obviously, so each standard deviation essentially is about 34% of the data. Holmes, shh. Sorry. So let's go to our next example. I feel like I may have told you that example 3 was the last example. I apologize for that. Surprise, there's another one. So we have a table here that shows the results of a survey that asked men and women how many pairs of shoes they own. First, we want to make a double box and whisker plot to represent this data. So the good thing about this table is it already gave us the minimum, the maximum, the first quartile, the median, and the third quartile. We already got all the information. We just got to put it on this graph here. Once again, I don't know why these numbers are like off to the side. They should be, hold on guys, sorry. Sorry, the garbage men are outside and the dog kind of goes crazy, so we'll just have to deal with it for a little bit. So we have all the information. All we're going to do is put it into our order. So our first box and whisker plot, I will make men and women. Got the men first here. Our least amount for men is 2. So it's going to be right here. Remember, this is 1, 3. I don't know why they're pushed over to the left. So it's going to be there. And then, so we've got our least value here. So I'll put a dot there. Our maximum for men is 17. So that's going to be right here. First quartile is 5. So that's there. Median is 7. So that's there. And third quartile is 10. So that's there. Let's connect it and make our box. Connect our box to our whiskers. And there's our men's box and whisker plot. Now let's do the women. Women's least value is 5. So that's going to be here. Maximum is 24. So that's going to be here. First quartile is 12. So there. Then 14. So there. And 17. So there. Make our box. Connect it to our whiskers. And there we have a double box and whisker plot. We also want to describe the shape of each distribution. For our men, it looks like we have a long tail off to the right. So that's going to be skewed right. For our women, it looks pretty much like both tails are equal and we have our median almost right there, smack dab in the middle of our box. So our women are going to be symmetrical. Now, we want to compare the number of pairs of shoes owned by men to the number of pairs of shoes owned by women. In looking at the median, which is our measure of center, a measure of center, and the mean, we can see that the median for women is double the median for men. Looking at the mean, another measure of center, we can see that the women is still greater than the men's. So from this, we can conclude that women own more pairs of shoes than men. I mean, you can kind of see it on the box and whisker plot as well. The greatest number versus the greatest number. Most of the data skewed on the men's, leaning towards not owning as many pairs of shoes, where most of the data for women is higher than that. Part C, about how many women surveyed would you expect to own between 10 and 18 pairs of shoes? So this is where it gets interesting. The women's mean is 14. And the standard deviation is 4. 14 minus 4 is 10, plus 4 is 18. So 10 to 18 is within 1 standard deviation of the mean. So we would expect 68% of women to own between 10 and 18 pairs of shoes. Because if we looked at our previous, 68% of the data lies within 1 standard deviation either direction, to the right and to the left of the mean. 1 standard deviation to the right and to the left is 10 to 18, so 68% of the data is going to lie there. But we didn't ask what percent. We asked how many of the women. Well, 68, how many women are there total? There are 40 total women. So what is 68% of 40? 0.68 times 40. It was about 27 women. So we can say that about 27 women will own between 10 and 18 pairs of shoes. So that is how you can use the standard deviation to apply it to your data sample. Box and whisker plots were from 11.2 lesson. This is from our measures of center, which we had earlier today, and then we've got our standard deviation, which we just did. Okay, so that's that.